In this section, we're going to study the hyperbolic functions. And I want to begin by just sort of saying there's a construct that we can do with this that we can do with really any function. And so I'm going to start with that. That given any function, and I've got this sort of wild function that has really no symmetry to it. And I'm going to create two other functions that have even symmetry and odd symmetry. So I am going to create a new function. I guess I'm going to call it r of x, that is going to be f of, let's see, I've got to use this. F of x plus f of minus x. And that's going to be an even function. And then I'm also going to create, let me make this a different color. And then I'm also going to create another function, I guess it's going to be called f of s of x, that is going to be f of x minus f of negative x. And so this becomes an odd function then. So given any function, we can create an even function from it, and we can create an odd function from it. Now, the canonical way to do this is not actually to do these functions, but 1/2 of those. So if I do 1/2 times that, and the other one is also going to be 1/2 times that. And that does a couple of things. One is that, hang on a moment. One is that r of 0 should be the same as f of 0. Let me see if that's true. Yes, r of 0 should be the same as f of 0. And then also adding these two functions should give you f back. And so this is the canonical way of what we say is basically separating f into an even component and an odd component. We can see these as like an even and odd part of any generic function. Okay, so the standard, this section 3.11 actually deals with doing this with the exponential function base e. So if I do, so this is my odd adaptation of the exponential function. So 1/2 of e to the x minus e to the minus x. And we call that the hyperbolic sine function. And sometimes this is actually pronounced sinh. And then the even function that we build off of the exponential, so e to the x, like 1/2 of e to the x plus e to the minus x, is the hyperbolic cosine function, and we call it cosh sometimes. And then if we take the hyperbolic sine function divided by the hyperbolic cosine function, now my 1/2s actually cancel out here, then that gives us the hyperbolic tangent function. So I can define hyperbolic, tangent, secant, cosecant, and cotangent basically in terms of sine and cosine, similar to how we relate the all of the other trig functions to the regular trig sine and cosine. So we have the hyperbolic cosecant. The hyperbolic secant is 1 over hyperbolic cosine. The hyperbolic tangent is 1 over hyperbolic... the hyperbolic cotangent is 1 over hyperbolic tangent. And so, yeah. And they're all based on these exponentials. It might seem a little strange that these are defined in terms of the exponentials, but we will see some bits of why they actually matter. So you might wonder, like, why are they hyperbolic, and why are they, why do they have names related to the trig functions? So the trig functions are sometimes referred to as actually circular functions. And so, there's circles and hyperbolas are two conic sections. And so something that is related to the circular functions, and I don't actually have it set up right now. I should have done that, but I didn't. So if you take a hyperbola, this hyperbola is x squared minus y squared equals 1. Oh, I should have mentioned there is this hyperbolic identity. There are these hyperbolic identities that are very similar to the circular identities. So for one thing, this says that the hyperbolic sine function is an odd function. The hyperbolic cosine function is an even function. And there's the, your Pythagorean identities for trig functions, that's cosine squared plus sine squared equals 1. Here we have cosine squared, or hyperbolic cosine squared minus hyperbolic sine squared equals 1. And to prove this, you basically just go back to the definition of what are the hyperbolic cosine and hyperbolic sine. So you can prove that this is true based on their definitions, and then also that this identity is true, that 1 minus the hyperbolic tangent squared is equal to the hyperbolic secant squared. And then there's the sum formulas for hyperbolic sine and cosine. And so since the hyperbolic sine and cosine satisfy this identity, that is basically a hyperbola. So if you think of the cosh of some variable t as an x-coordinate and the sinh of some variable t as the y-coordinate, then they lie on this hyperbola x squared minus y squared equals 1. Okay? And it turns out that if you pick any point, which is defined by some t value, and all of these really only lie on the right side hyperbola. This hyperbola should exist on both sides of the y-axis. But so if you take some point that's on this curve, it turns out that t over 2 is the area drawn out in this section. And this is also, like, you can draw a similar picture for circular functions where, if you have cosine squared plus sine squared equals 1, so cosine t and sine t can be seen on a circle, and the t over 2 is actually the area of a circular sector in there. Anyway, there's a lot of kind of analogous behaviors between the circular functions, which we think of as our regular trig functions, and these hyperbolic functions. So they do satisfy these identities, and then you can also go back to the original definitions in terms of E and find that the derivatives behave pretty similarly, but like slightly differently in relation to each other, to how the circular function derivatives behave. So in this case, the derivative of sinh is cosh, and the derivative of cosh is sinh. Whereas in the circular case, there would have been a minus. The derivative of cosine is minus sine. But yeah, so these are the derivatives of those. in this section, I think it's important to see that these functions exist, and to also kind of recognize that this is a thing that you can, that making these even and odd functions is a thing you can do with any functions. But also that these hyperbolic functions will actually appear occasionally out in the real world. In particular, if you happen to be an engineer, you might really care about the hyperbolic cosine because it actually shows up as being the curve that is created by a free hanging chain. And so that is quite relevant. But the big thing is just to, you can use this section as a way of exploring a new type of function that we haven't been exposed to before, and playing with some of the derivative rules for this new definition of a function.